Hello, and we go on with problem number 5 with this interesting system of transcendental equations with cosine function. So let me present the solution. So we have cosine of first unknown x1 equal to x2, then cosine of x2 equal to x3 and so on, and cosine of the last xn is equal to the first unknown x1, so cyclically. So how to proceed? Let me first show what happens if n is equal to 1. If n is equal to 1, then we simply have the one equation, cosine of x is equal to x. We cannot solve this equation, that's why I said a transcendental equation algebraically, but we know by simple analysis of the graphs and behavior of those functions, then cosine x is like this is 1, this is p over 2, and so cosine is like this. This is graph of the function on the left, and on the right we have a simple linear function under the angle of 45 degrees. And so those graphs intersect only on this one point, and this x0 coordinate is actually the only solution of this equation. And now we are going to show that we have n greater than 1 when we have a system, then x1 will be actually equal to x2, will be actually that all unknowns will be equal, and that it will be equal exactly to that value x0 here. So how to conclude that? Let us first show what happens if n is equal to 2. Then we have cosine of x1 equal to x2, and cosine of x2 is equal to x1. And if we substitute this here, we obtain that cosine of x1 is equal to x1. And if we put this instead of x1 here, we obtain that cosine of x2 is equal to x2. So we actually see that x1 and x2 satisfy the same equation actually, that if the solution is unique, then x1 will be equal to x2. So what happens in the general case? So we will denote this as cosine with 2 in parentheses, so to distinguish from a cosine square. This is not cosine squared, but cosine of cosine, so the composition of two cosines. So in general, we will have cosine of cosine n times, and we will denote this as cosine n in parentheses. So in this general situation, we will again obtain that cosine to the n times of x1 is equal to x1, and that cosine n times of x2 is equal to x2, and so on for all unknowns. And now, so in general, we will now look at this equation, cosine n times of x equal to x. We will show that this equation has a unique equation, and that equation, unique equation, exactly the same x0 as pictured above. So why is this so? So let me show first that x0 is actually a solution of this, because this can be written as cosine of cosine of cosine n times of cosine of x equal x. And so if we put this x0 here, x0 here, we actually know that cosine of x0 is x0. And then we have the cosine here of x0 is actually x0, and so on and so on. We simply see that we will now finally have cosine of x0, which is x0. So we will have x0 on the left and x0 of the right. So x0, x pictured above, this coordinate here, is actually indeed a solution of this equation here. And we will now prove that this is the only solution. We can write this, and if we prove that this is only equation, we will obtain exactly, okay, let me write this now in red. We will exactly obtain that all unknowns are equals, because of unknowns satisfies the same equation with this same unique solution x0. So we can write this equation as x minus cosine n times of x equals 0. And we will denote this as function fn of x. And we actually need to prove that this function has only one, 0 point, only one null point, so that it is equal to 0 at only one point. And actually we will prove that this function fn is strictly increasing. We don't know how this function looks, but we know that if we take this in coordinate system, this function, we know because of this cosine is always bounded between -1 and 1. So this x, because of this x, we know that when x is going to plus infinity, that our function is also going to plus infinity. And if x is going to minus infinity, that our function is also going to minus infinity. And we only need to prove that this function is strictly increasing, and if it is strictly increasing from minus infinity to plus infinity, and of course differentiable function, so continuous function, it will have actually one null point here. This will be as shown before x0. So we will simply look what is the derivative of this function. We have fn of x is equal to x minus cosine of cosine of cosine n times of x, cosine of x. So what is the derivative of that function fn prime of x? Derivative of x is 1, and derivative of cosine is minus sine, so this will be plus sine of cosine n minus 1 times of x. We are now using simply a product rule for actually the rule for derivation of composition, yes, product rule. So this is derivative of this first cosine, then derivative of the second cosine is minus sine of cosine n minus 2 times of x, and so on, and finally the last cosine will have derivative minus sine of x. But now we know that sine is as cosine already stated above. This is between minus 1 and 1, and this is between minus 1 and 1, and the last one, all those terms are between minus 1 and 1, and the product of these terms are also between all those, all that product of n terms is also between minus 1 and 1. And we have 1 plus something that is between minus 1 and 1, so we know that fn of x derivatives is always greater or equal to 0. So we know that this function is increasing. We still don't know that it is strictly increasing, but sine of x is equal to minus 1 and 1 in discrete number of points, in only countable number, discrete countable number of points. So this first term can be minus 1 or 1 only in this discrete number of points, and all those terms should be minus 1 or 1 that we can expect to happen, that these derivatives can be equal to 0. So this derivative is actually greater than 0 except in discrete number of points. In only discrete number of points it can be equal to 0. So this means that it is indeed strictly increasing, and we have proved what we have just proved what we claimed. So thank you very much for your attention. See you soon in the solution of problem number 6.